scenario space. And there's a few questions, I guess, that we've been asking ourselves that we would really like to address also in this session. So one is really to get a bit of an overview of efforts around quantitative representations of adaptation and adaptive capacity, because it's still an emerging field. There's quite a lot of approaches, but they're quite dispersed, so really to bring those together a little bit. We'd also really like to discuss a little bit how the indicators that people are working on in specific sectors for specific regions can really be operationalized to be much more useful in the scenario space. And then finally, since of course the IAMs, the integrated assessment models, play a really, really important role in this whole space, to really discuss a little bit what entry points could really be of how to better represent adaptation in these models and what adaptation would need to look like kind of to be able to be integrated there. We have 5 speakers today. We've asked them to kind of limit their interventions to 10 minutes, and we'll have a short space for clarification questions, just briefly, and then would really like to have a bit of space for discussion in the end. Just to make sure we're all on the same page of what we're actually talking about, just briefly the Ipcc definitions of adaptation and adaptive capacity, where adaptation is understood as the process of adjustment to actual or expected climate and its effects. So really, a response measure to this, whereas adaptive capacity is understood as the ability of systems, institutions, humans, or other organisms to adjust to potential damage and take opportunities or to respond to consequences. As I said, we would really like to have a little bit of space for discussion afterwards, and these are just a few questions that we would love for all of you to keep in mind during the presentations and to maybe come back to, but obviously, there's plenty of more questions also to be asked. But one point that I also mentioned in the beginning that we'd really like to reflect upon are the main motivations of why to include adaptation in integrated assessment models, and really to maybe to reflect a little bit critically also what the benefits are, but also what the potential issues might be, or if there might even be pitfalls of including adaptation in IAMs. But as I said, also really kind of practically discussing what entry points for adaptation might be in IAMs, and then also understanding kind of the scaling potential of some of the more sectoral or local approaches to modeling adaptation to be reflected in the global scenario space. And with that, I'll leave the floor to our speakers, and I would really like you to join me up here for the presentation. So we'd really like to have our panelists up here, and if I can invite you to come up. But our first speaker is Vanessa Folz from the Global Climate Forum in Berlin. And while we're getting set up for the presentations, I think you have this. Hopefully if we can get the first presentation, perfect. Then I will hand over this clicky thing to you. And
just click here forward and backward.
Yes.
Okay, perfect. Thanks. Great. All right. Hi, everyone. My name is Vanessa Folz, and I would like to present my recent work about using learning scenarios to quantify future adaptation to you with this presentation. So the damages occurring from flooding due to sea level rise are one of the costliest damages or impacts of climate change. And it's really challenging to adapt to it because at the same time, there's a wide uncertainty in the projections about future sea level rise. So it's very uncertain how much sea levels will actually rise in the future. And in order to deal with this problem, what decision scientists do in the literature is they use a lot of flexible methods. For example, the Adaptation Pathway Map that you can see here. So the idea is basically that you have a different set of actions and you can decide for one, but over time, as the actual development of the climate variable takes place, you can still move between the different actions and change the measurement that you want to go with. And there's another method called real option analysis that has another crucial benefit, namely it anticipates future learning in the future that will take place, so the future learning about the variable development you're looking at, and it incorporates this learning in the decision analysis. And it uses learning scenarios to do so. We can already see a learning scenario right here, which is a discrete and directed graph. And when we use wheel option analysis, we can, for example, justify additional costs for flexible adaptation options. And in this presentation, I would like to briefly show you how the learning scenarios actually work in the decision analysis, and also how we can create the learning scenarios, and why the traditional method of Cox, Ross, and Rubinstein to create learning scenarios is not a good option if we deal with climate uncertainties. So let's start with a simple example to understand the learning scenarios. Assume we are a very risk-averse coastal decision maker and we have 3 different options to choose from. We can either A, build a 1 meter dike, B, build a 2 meter dike, or C, build a 1 meter dike with the upgrade option, so simply a dike with a wider foundation. And then if we decide to upgrade this 1 meter dike to 2 meters, it's a bit easier and cheaper if we have the wider foundation in the beginning. And we also see different costs with the different actions on the left side of the slide. So we see it is a bit more expensive to choose action C, the 1 meter dike with the upgrade. And now we will add the learning scenario in this setting. So we have now again a directed discrete graph plotted over time and the sea level rise. And now, of course, this is very simplified, but we now have a certain learning occurring in this graph that we observe the actual sea level rise until 2060. And depending on the actual sea level rise we will observe in the future, we have different projections for the further future until 2090. And we can now use this learning scenario and calculate the average costs occurring in the future for each action we choose today. So for example, if we decide to go with dike A and implement the 1 meter dike, we have a 50% that in the future we observe low sea level rise in 2060, and then we know this 1 meter dike is efficient until the end of our time horizon, and we don't have to do the upgrading to dike B, and the total costs are $1. But there's also the other 50% chance that we observe high sea level rise in the future, and then we actually want to upgrade and then transfer to action B and top on the 1 meter dike to have a 2 meter dike, and then the costs are $3. So on average, action A will give us $2 of costs in the future, and we can do the same for action B and C. And in this case, we see that action C is actually the cheapest option to go with. So using the wheel option analysis in this case, we've justified the additional costs in the beginning for action C. And of course, the result of this decision analysis depends on the learning scenario, right? So imagine it looks a bit different like this. We just have an additional arc. And now the future learning we have, if we observe low sea level rise in 2060, is that we cannot rule out that sea levels will stay below 1 meter, and then we always have to upgrade to the 2 meter dike. And this simply changes our average cost structures, and in that case, action B would be the cheapest option to go with. So this is the basic idea of learning scenarios, and the question now is how do we actually create the learning scenarios, because they are not officially provided, for example, from the Ipcc. So what decision scientists generally do is they generate them themselves, and they construct them based on static projection. Now you can see here a static projection of sea level rise. It's from the assessment report 6, and the static projection here is a probability distribution function looking into the future from today onwards. But what we actually want in a learning scenario is that we can look into the future in future moments in time. So what we do now is we construct the learning scenarios on top of the static projections. And I would like to present 2 different methods to do so. So the first one is by Cox, Ross, and Rubinstein on the upper part of the slide. So the idea is you have then you fit a stochastic process onto the static projection, and then based on the parameters of the stochastic process, you can generate the lattice or the directed discrete graph that we can see on the right top side of. And now the method by Cox, Ross, and Rubinstein is originally stemming from finance economics. So it was originally designed to model stock market developments, and they have a constant growth assumption in every year. By using the geometric Brownian motion as the stochastic process, we assume the same constant growth in every year, so we have an exponential growth. As we can already see in the picture here, the exponential shape of the lattice is not a really good fit on top of the static projection, which is why we created another method called direct fit that we can see of the slide. And the idea is that we first design the structure of the lattice, and in the second step, we position the nodes of the lattice directly on the static projection. So we are very flexible and try to mimic the uncertainties of the static projection. And we can see it in the picture that it appears to have a better fit. And now I would like to present a more detailed analysis of how good the two different learning scenarios actually represent the static projection. And we see this right here. So we did a Monte Carlo analysis. So we simply draw a lot of realizations, pathways running through the lattice 10,000 times. Take this data, and from the data we can calculate the quantile values. And here we plotted the quantile value function from the Ipcc data in yellow, and in blue is the learning scenario on top of it. And we can already see that on the left side, the Cox, Ross, and Rubinstein method is only a good fit in the last time step, but before that it really has a big gap. And the direct fit method fits a bit better. We also quantified the gap between the two probability distribution functions. We used the Earth mover distance to do so. So the Earth mover distance is really just a gap between two quantile values, and we determine the average distance, meaning we take the gap for all different quantile values and for all different time steps, and then we have the average value. And this is the result of it. So the average distance on the left side is 19 centimeters between the two probability distribution functions, and the average distance on the right side is only 6 centimeters. So it's really confirming what we can already see in the pictures. What we cannot see in the pictures is how big the gap is for the fat tails of the distribution. So for the quantile values below 5% and above 95%, because I only plotted the 66% uncertainty range. And there we see that the gap for the Cox, Ross, and Rubinstein method is even bigger, and again smaller for the direct fit method. So concluding from this, we can say that learning scenarios constructed through the method by Cox, Ross, and Rubinstein are maybe very suitable to model stock markets, but generally it's not a good fit for climate uncertainties, as we've seen for the example of sea level rise. And instead we can use the direct fit method that has a way better goodness of fit, especially for the fat tails. Plus it's easier to construct because we skip the stochastic process. And in general, we have seen that if we want to quantify adaptation decisions, it's good to use learning scenarios because we can justify additional cost for flexible adaptation measures, and then maybe we can reduce the adaptation cost depending on the learnings that will occur, but there is definitely the option to end up with lower adaptation costs if you consider future learnings. Thank you for your attention, and I'm happy to answer any questions that you might have right now. Yes?
So sea level rise seems it's perhaps on the extreme end of the scale of potential impacts in terms of the the inertia of the climate system, and in terms of perhaps the scenario independence of the extrapolation. How have you thought about how you would adapt the approach when you also have to take into account like the effect of rapid mitigation and a change in direction of the impact variable, which you might not see in sea level rise, but you might see in heat wave risk?
I see. Well, that's actually nothing I considered so far because we are really focused on coastal adaptation and sea level rise. But obviously the approach that I presented, the direct fit method, is only suitable if you have a slowly increasing change rather than a rapid change in the climate variable. So that's a really good point. That is the assumption. You have to check if this is valid for your climate variable before you want to apply the direct fit method. That's for sure, yeah.
Thanks.
Welcome.
Hi, my name is Laurens Spilman from Rocky Mountain Institute. Thanks for an interesting talk. My question was actually fairly similar, which is, what if there are specific tipping points that will be hit? What if the shape of the uncertainty is not the shape that you see within those kind of model projections? So what the flexibility would be in the approach there? So how would the learning method be valid if actually sea level rise takes a more rapid turn, for example?
Yeah, I mean, definitely if you have specific tipping points and want to address rapid change, you would need a different structure in the ladders than the one that I presented.
Great. Thanks a lot for this really, really interesting presentation. I think any further questions or discussions, we'll just hold on to those thoughts, please, and we'll have those after the rest of the presentation.
Thank you.
Thanks a lot. Yeah. So great. Yeah. So.
So it's Eva. No?
Yeah. Okay. If it's okay for you, we'll just switch the order because we have that presentation. Okay. Well then, we have Eva next from the University of Graz. Thanks a lot. The floor is yours.
How do I? Just the green button? Yes. Okay. Okay. So I'm going to present our work on the macroeconomic and budgetary implications of public climate change adaptation pathways for the cases of Austria, Spain, and the Netherlands. So to briefly introduce you to this topic, we see that in many macroeconomic model-based assessments of future climate risk, economic losses are quantified, occurring from capital destruction or changes in sectoral productivity levels through different climate impact chains. This also puts a strain on public budgets due to changes in the tax base, but also as the public sector is paying disaster relief payments to affected households and the private sector. This literature generally concludes that adaptation is necessary and identifies a clear role of the public sector in reducing future risk through adaptation by providing critical infrastructure and enabling private adaptation and acting as an information broker. However, policy costs of implementation arise, requiring a reallocation of public expenditures. We see in most of these macro models, there's still a rather generic and unsystematic representation of adaptation, which limits the capacity of these models to develop and assess adaptation pathways that we find in practice or are developed. And also this omission biases estimated climate change costs. I want to emphasize this last point by introducing this figure by the UNEP Adaptation Gap report that nicely shows the trade-off between the stringency of adaptation and the level of residual risk that society and economy faces where residual risk emerges due to soft and hard limits of adaptation or due to ineffective or insufficient adaptation. We try to contribute to this literature by explicitly considering different adaptation options, so differentiating between infrastructural, ecosystem-based, and informational measures, and implement them as part of comprehensive adaptation pathways, as brought forward by Marjolein Haasnoot and co-authors. We've already seen in the previous presentation, and assessing the macroeconomic viability of public adaptation actions and their effect on the income and expenditure side of public budgets. And then quantify the adaptation effectiveness across climatic and socioeconomic scenarios. So the first step of our analysis was the identification of adaptation cost pathways. I don't want to present all three of them, but only exemplify for the case of the Netherlands. So we looked at average annual expenditures on adaptation on river and coastal flooding as implemented through the Delta program. And we extrapolated these costs based on the annually updated figures disclosed by the Delta Commission. And then we also consulted with experts from the National Delta Commissioner's Office to gather further information on expenditure categories and which types of measures and maintenance costs are expected. We then introduced these adaptation cost vectors into a macroeconomic model. So a CGE model, a static multi-regional model calibrated to the GTAP9 database with a high regional resolution at the EU level and 5 regions representing the rest of the world. Overall, we have 20 economic sectors represented by nested CS production functions, where final demand in EU regions is represented by 2 agents, namely a representative regional private household and a regional government. Also, we assume a fixed tax rates and a balanced public budget such that revenue is equal to expenditure. We implemented climate change impacts quantified by different biophysical impact models by changing productivity levels in the private sector through agricultural productivity changes or impacts in forestry, but also considered the destruction of capital stock and the change in government expenditures. Adaptation actions were considered depending on their type. As I said, we differentiated between structural, ecosystem-based, and informational measures, where, for instance, structural measures such as the additional investment costs for constructing seawall was introduced by the increase in the investment level of the public sector and an adjustment of the overall government demand. And this brings me to the results. I'm showing the results for SSP2 4.5 scenario combination. You can see for Austria and Spain here, looking at impacts on productivity level in the forestry sector, which basically perpetuates throughout the Austrian economy, reducing overall GDP by about 0.6% in the impact scenario, so in the darker bar. And also reduces welfare levels, however, to a lesser extent due to the substitution possibilities of the private household. We see in an adaptation scenario that these effects are mitigated to a significant extent, and also in the Spanish case, where we see the productivity changes in the agricultural sector perpetuating throughout the economy can be largely reduced by adaptation. And we show the different benefit-cost ratios implied are indicated by the brackets. For the case of the Netherlands, the story is a bit more ambiguous. Given the extremely high protection levels pursued under the Delta program, we find that the cost of implementation exceed the benefits from avoided damages if we only look at low impact floods or expected average damages. However, we see here that if we look at the consequences from a 1,000-year flood, GDP effects are significant. And if we look at the benefits that fully unfold by 2050 from the Dutch Delta program, these consequences can be largely avoided. We find that on the public budget side, these effects are reflective of the macroeconomic development, where we find that an absolute reduction in public spending occurs in the impact scenario, meaning that a reduction in the transfers to private households, in the provision of public services and other government consumption, which can be largely reduced if we consider adaptation to take place. Same holds for Spain, and also for this severe case in the Netherlands. To conclude, and some prospects for further research, we find that economy-wide benefits from adaptation arise despite the costs of implementation. And overall, we see on the budgetary side that adaptation creates fiscal space, such that a higher level of public good provision and transfer payments is possible compared to a no adaptation scenario. Also, our results are robust across the range of benefit-cost ratios of adaptation implied. And we also see from the case of the Netherlands that protecting against low probability yet high impact events is costly, but so is damage compensation and the loss of capital-intensive industries in floodplains. Also, we find across all our scenarios, residual damages remain and depend on the climate signal and adaptation effectiveness. And we see this especially when we look at results for RCP 8.5, which I have not shown you here, but we ran also this scenario. For further work and how we want to continue on this study, we want to capture a more detailed resolution of these socioeconomic development pathways across SSPs. So far we imply SSP development, we extrapolate based on GDP developments, but we want to go in a more sectoral, look at this from a more sectoral perspective and explore adaptation pathways also across different SPAs, so shared policy assumptions, and move beyond these adaptation pathways that we have now computed based on current adaptation expenditures, and also challenge this assumption of linear adaptation benefits that we largely rely on now, considering also hard and soft adaptation limits, especially as we approach higher warming levels. And this is it from me now. Thank you.
Any clarification questions? Yeah.
Hi, great talk, thank you. My name is Justin Johnson, I'm from the University of Minnesota. That's great to see the inclusion of riverine and coastal flooding damages in there. I just wanted to ask if you could share more information about how you went from the expected change under the scenarios to, it sounded like it was through depreciation of capital stock. I maybe missed that, but if you could give more details how you track from the flooding to the impact on the economy, that would be really great.
Okay, so the impact channels, basically, I need to get back to this slide. So we have the biophysical impact models that basically, there we are, that basically tell us the total capital stock that is damaged through coastal or river floods. So we model, or we include this in our model via just the damage to the capital stock. So this disrupts the production in the economy and thereby perpetuates into these GDP losses. So capital-intensive industries are relatively affected more, but due to this Walrasian equilibrium that we imply in our model, this spills over. Yeah, I hope this is clearer now.
Okay, I see no more questions for now. Then we can continue with the next presentation. Let's see who it is.
Oh, I should.
Okay, then we have Kai.
Hi, I'm Kai from the University of Edinburgh. So today I'll talk about my work on the projection on health-related adaptive capacities to heat and cold in the UK. So heat can affect our health multiple ways, and some of them you may have already felt today, and you may feel weak, and it may also affect our cardiovascular and respiratory systems, and also it can also affect our health indirectly by affecting the health service and causing accidents and affecting infrastructure. And similarly, cold can affect our health as well, but I'll not go into depth here. And this figure, you could see the increase in daily deaths in Athens and South Finland under different daily mean temperatures. And you could see that under similarly low temperatures, there is a sharper increase in daily deaths in Athens than in South Finland. So this may be related to regional acclimatization and also adaptation, which I'll talk a little bit more in a bit. So in addition to the regional difference, the impact can also change over time. So this is the relationship between relative risk of mortality and daily mean temperature in Scotland in the past 3 15-year periods. And on the left-hand side, you could see that the cold risk has decreased hugely to a minimum level in the recent 15 years. However, there is little change for the heat effect. This, again, may be related to adaptation, and this is why I'm working on this. So, my research questions are: what factors affect the adaptive capacities to heat and cold, and how they may change in the future under different socioeconomic levels in the UK? So my method is a rapid review followed by an online focus group, and we discussed the key factors that affect the health-related adaptive capacities to heat and cold, and also the projection methods and the SSPs. So the UK developed its own SSPs. I'm not involved in the project, so I'm nervously presenting this, and I'm aware that some of its producers are here in this conference. So the UK SSPs are both inconsistent with the global SSPs and also reflects country-specific features, and the products include a set of qualitative narratives under the 5 SSPs, and quantitative projections for 27 socioeconomic indicators and semi-quantitative projections for 50 socioeconomic indicators. So this graph shows an example of a semi-quantitative projection, and this is for income inequality. So the key factors that we identified that affect health-related adaptive capacities to heat and cold are economic status, so it affects multiple aspects of our lives and how people can prepare to respond to and recover from heat and cold. And in addition to this absolute economic status, relative economic status or inequality can also affect their adaptive capacities, because it can affect crime and violence, and also may affect social cohesion, so which is another key factor identified. So social network could provide support such as information support, emotional and instrumental, such as buying medicine and grocery when the temperature is too extreme for those vulnerable people to go out. And also, the availability of health service is a key factor, as the need for the health service may increase under extreme temperatures. And also, people's behavior are very important as well. So, for example, I'm living in a B&B in Vienna these days, and my host told me to only open the window in early morning and evening and keep the window closed and the shutters down in middays, so to keep my room cold. And here are 3 other factors that we identified. So in urban areas, people may be exposed to enhanced heat because of the urban heat island effect, and green space can mitigate this effect. And people spend a lot of time indoors, therefore housing and energy efficiency are important as well. Whereas in the past in the UK, it mainly focused on keeping homes warm, so there is a complexity there in terms of cold and heat effect. So afterwards, we conducted a focus group and we discussed the method to project the adaptive capacities into the future. And 4 out of 6 participants preferred the method to construct adaptive capacity indexes based on individual indicators and then project the index into the future because of its transparency of this method. And the heat adaptive capacity is the average of income inequality, social cohesion, healthcare, and public awareness, which is a proxy variable from the UK SSP project representing behavior I just talked about, and urban population and protected area, which is a proxy for green space. And for cold adaptive capacity, it has indicators including income inequality, social cohesion, healthcare, public awareness. And apart from urban population and protected area used for the heat, we used energy efficiency for the cold adaptive capacity. And here is our main result on the projection of heat and cold adaptive capacities in the UK under the 5 SSPs. So you could see that under SSP1, the adaptive capacity is the highest because of the lower income inequality, higher public awareness, higher green space. And under SSP2, there is little change in the adaptive capacity. This is because of mixed changes in those individual indicators. So the economy continues to increase slightly, but income inequality also increases slightly. And under SSP 3 and 4, there is a huge decrease in the adaptive capacity, whereas they may be driven by different reasons. So under SSP 3, the condition is worsened for everyone, whereas under SSP 4, it is driven by a few elite, whereas a huge body of poor. And under SSP 5, there is little change in the adaptive capacity again. So this is because the adaptive capacity is beneficial from the huge increase in economy for everyone and therefore a decrease in income inequality. However, social cohesion decreases because of individualistic lifestyle, and also public awareness in health and environmental also decrease. And also you could see that the adaptive capacity for cold is generally slightly higher than heat. So this is because the distinct indicators we used for cold and heat. So for heat, the distinctive indicators are urban population and green space. And urban population is projected to increase under all SSPs, and green space is projected to decrease under SSP 3, 4, and 5. Whereas for the cold effect, we used energy efficiency as an indicator which is projected to increase under all SSPs. So in the future, we're going to explore the potential to further downscale the projection to Scottish level and also link the adaptive capacities to the relationship between mortality risk and daily mean temperature, and then link it to temperature data and the climate change scenarios. So to project the mortality burden and the climate change and the aligned climate change and socioeconomic scenarios. Thank you.
Thanks, Kai. Do we have clarification questions? Not at the moment, then we have more time. Oh, yeah, then Marina.
Thanks. Hi, my name is Marina. Thanks so much for the presentation. I think I missed the part where you explained how you did the projections. If you could just do this in 30 seconds.
Yes, thank you. Yeah, this slide. So we constructed 2 indexes for heat and cold based on the key factors that we identified from the rapid review. And proxy variables from the UKSSP project were identified for those factors. And the UKSSP project provides data, semi-quantitative data and also quantitative data under the 5 SSPs into the future.
For example, specifically for public awareness, how is this measured in the future?
Oh, yes. So this is public awareness in environment and health. So by the UKSSP project, they held workshops with stakeholders, and they showed the projections of other factors based on the global SSP, and then and also the qualitative scenarios, and then the stakeholders were invited to draw their own lines and then have discussions to reach a consensus.
Thanks.
Okay, thank you, Kai. Then we move on to the next presentation. And now it's you, Esther.
Yes, thanks very much. So I think it's a nice combination of sectors, as I will present something on the climate change adaptations and impacts in agriculture and forestry within Europe, and how this could lead to a reconfiguration of land use, mostly within the agriculture sector. So as we all know, climate change is rapid, widespread and intensifying, but the impacts differ across regions. And that's not just the case for the world, but also within Europe. Within this study, we're looking especially within 4 main regions within Europe. First in the northern part, where it's especially storms, hot and colder summers are occurring, versus the south, where it's much drier and much more warming occurs, the western and the eastern part of Europe. So climate change impacts actually and adaptation interact a lot with different mitigation and adaptation strategies. So recently there have been a lot laid out within Europe. For example, the EU biodiversity strategy, the Fit for 55 package aiming towards more mitigation measures, as well as the farm to fork strategy that has different adaptation strategies. Given all those policies and strategies, it's pivotal to really focus on the unified role within the land-based sectors, and then within agriculture, forestry and land use in a sort of integrated manner. And with this, we could answer or try to answer some questions regarding how the climate change impacts vary across regions and sectors in Europe. What are biophysical and economic integration strategies, adaptation strategies, and how does climate change affect the interlinkages between those socioeconomic sectors. So for this, I'll use an integrated assessment modeling framework, first focusing on the climatic impacts, which takes both global climate models as well as regional climate models into account. Then I use different biophysical models, the global gridded crop model EPIC, the more detailed European gridded crop model IIASA, and the global forest model G4M. Finally, these are being translated in terms of productivity shifters and input shifters into the global economic model GloBIOM, which is then detailed for Europe, so for GloBIOM EU. And we would especially focus then on what happens in terms regionally differentiated within Europe and both into the rest of the world in terms of the changes in production, area, yield, as well as prices, and trade and land use. So first starting from the sort of more climate or biophysical perspective and focusing on the different crop models, we use the model process-based global gridded model IIASA to assess the main agricultural systems in response to climate change. And within these panels, you can see on the upper part for wheat and on the down part for corn, where you could see that this is very contrasted by different biophysical, by different crops. So the impacts are much worse for corn than they are for wheat. And we could generally see that this worsens with a higher RCP, an RCP 8.5 compared to a 4.5, and generally much worse in the south compared to the north. So how to make sense of this? First, we start to then group these agricultural crops into common denominators in terms of how they would impact towards certain climatic variables. So we distinguish C3 summer crops, C3 winter crops, C3 tubers, and C4 crops. So the C3 summer crops are marked by a high temperature requirement and a strong CO2 response, and have rice, flax seeds, and green fodder, for example. C3 winter crops are mostly grown in the winter season and have a strong CO2 response as well. C3 tubers are, for example, potatoes and sugar beets, and have a long growing season but are less sensitive to CO2. And C4 crops also have a long growing season but are less sensitive to CO2. So this is mostly corn and silage corn. And you can see that overall in Europe the impacts are actually not so contrasted, but when you look by crop group, which are the first 4 panels, you see much more differentiated patterns. For example, within those C4 groups, whereas there is the south and the north differentiation, and the C3 winter crops, which are actually beneficial for Europe as a whole. So then moving on towards the more towards the adaptations. In this study, we focus actually on more autonomous adaptation, so not really policy-driven. In terms of adaptation, we have adaptation at the producer level, which we differentiate in 3 different types. First, an area reallocation to crops in a certain region. Then a change in the management system, for example, going towards higher inputs or going towards irrigation. And then a change in the rotations in which crops occur. So, for example, replacing some weeds with some corn crops within the biophysical possibilities. So under RCP 4.5, we would especially see a decrease in the arable land because in Europe as a whole, because of this overall productivity gain. However, this is reduced to a large extent under RCP 8.5. This is mostly due to the CO2 fertilization effect. And this is partly compensated with an overall effect on crop yields. And this positive impact of climate on crop production ranges from 12% to 4%, considering adaptation under an RCP 4.5. Now, if we focus more into the different regions within Europe, then we could see this differentiation between the north, the south, the west, and the central east. And we would see that in the north, there is especially this momentum or this gain towards C3 winter crops compared to C4 crops, so mostly the maize and corn-based systems, and a decrease into the tubers, so the potatoes and the sugar beets. And this, in the south, we see a pattern in the other way around. So there's an increase in the C3 tubers and a decrease in the C4 crops. This C3 winter actually gains everywhere in Europe because it becomes more viable to grow, especially within Europe. Actually the adaptation strategies are not limited to the farm level, but also occur at the market level. So if we look into the trade patterns, then we could see by the size of the trade that under an RCP 4.5 scenario, the trade actually decreases because of this positive effect of climate. However, this increases again under an RCP 8.5. And we can see that actually due to this intra-regional trade within Europe, there is some specialization towards this C3 versus these tubers. And this in turn actually decreases a bit the self-sufficiency on specific agricultural items within certain regions in Europe. Now, if we look at the forestry sector, then we would see that, that especially due to the CO2 fertilization effect, this increases across Europe, but also mostly into the northern parts of Europe. Because of a lack of time, I have to go quickly here, but especially here in the RCP 8.5 and in the northern part of Europe, we could see that there are these increases in sort of the increment of the forests, whereby sort of less area of forest needs to be locked. However, due to the conservation policies in Europe, we still assume that we cannot the forest land cannot actually be converted and therefore doesn't have this competition with, for example, agriculture. Overall, in terms of the economic and environmental impacts, we see that under an RCP 4.5 scenario, there are these benefits for both consumers and producers because of this extra productivity gain. However, these decreases, especially under an RCP 8.5, both in the forestry and the agriculture sector. And especially for crops such as maize, you would see this very high impact on the prices. So in terms of the more environmental impacts, we would see a decline in the managed forest area, and we would see a turn towards a decrease, a small decrease in cropland area. But this decrease in cropland area actually goes towards an increase in intensification, mostly towards high input systems. So just to conclude, we would see that actually the magnitude of climate impacts on productivity changes highly differs by land use activity, giving rise to adaptation at the producer and as well as at the market level, leading to trade. And an increase in intra-regional trade within Europe. And this decreases a bit the self-sufficiency within certain regions in Europe. However, some of the caveats here is that we didn't consider actually the more variability in the extreme events, which would have actually a higher impact on actually the climate impacts and the potential losses and certain adaptations such as trade. And with that, I would like to thank you very much for your attention.
Thanks, Esther. Maybe we have time for one short clarification question. Yeah?
Thank you. Really incredible amount of work that has gone in here. That's clear. and an impressive amount of models that you used as well. I have one question. It almost sounds like you took like a behavioral approach, an agent-based approach with the decisions that are made on a producer level. And I was wondering, like, what is kind of the implicit idea behind that or philosophy behind that? Are they profit maximizing, or how? Like, what's the logic behind that decision making, or implied decision making?
So, okay, I'll try to answer very briefly. Unfortunately, this is not the case. So the model we used is a partial equilibrium model. So it covers the agriculture and the forestry sector, and basically it optimizes the producer and the consumer welfare by optimizing land use and land use change. So you wouldn't have any, so it's purely profit-driven, as you say. You would not have any early adopters or any social decisions taking into account. So it's based on the relative profitability compared to other regions in the world, basically.
Thank you so much. Then now we have an online presentation.
Part of the INFORM team at Joint Research Center of the European Commission in Italy. I'm going to briefly present the INFORM Climate Change Risk Index, the latest product of the INFORM suite. The title of my presentation is Assessing the Enhanced Coping Capacity Required to Counteract the Adverse Impacts of the Amplified Climate-Related Hazards. INFORM is a multi-stakeholder forum for developing shared quantitative analysis relevant to humanitarian crises and disasters. INFORM is developing a suite of quantitative analytical products to support decisions at different stages of disaster risk management cycles, specifically prevention, preparedness, and response. The INFORM Risk Index is for prevention and preparedness. The INFORM Severity Index supports mainly the response. INFORM Warning is in development and will monitor early warning signals to support preparedness and early action. And the INFORM Climate Change is designed to show future risk and help to align adaptation and prevention measures. All INFORM products follow the same principles. They should be global, open, reliable, and flexible. The INFORM partnership includes organizations from across the multilateral system, including the humanitarian and development sectors, donors, and technical partners. The Joint Research Center of the European Commission is the scientific and technical lead for INFORM, and United Nations Office for the Coordination of Humanitarian Affairs, OCHA, is the coordinator. FCDO and European Commission are the major donors. INFORM Risk is a global open-source composite indicator which measures the risk of humanitarian crises and disasters of the countries. INFORM Risk model is based on risk concept. It uses 80 different indicators to measure hazards and people's exposure to them, including all main type of natural and human hazards, vulnerability, and resources available to help cope. INFORM Risk creates a risk profile for every country. Each has a rating between 0 and 10 for risk and all of its components, so it is easy to compare. The INFORM Climate Change Risk is an upgrade of the INFORM Risk, and it shows how INFORM Risk will change in mid and late 21st century. The overall objective of the INFORM Climate Change Risk is to develop a common evidence-based tool for risk-informed decision-making that can help unify disaster risk reduction and climate change adaptation strategies. It includes climate, demographic, and conflict projections based on representative concentration pathways, RCPs, and shared socioeconomic pathways, SSPs, introduced by Intergovernmental Panel on Climate Change, IPCC. RCPs are time series of emissions and concentrations of the full suite of greenhouse gases, while the SSPs are set of future pathways of societal development, including population, education, urbanization, and economic growth. These scenarios are used to project the hazard and exposure dimension of the Informed Risk Index into the future, taking into account changes to climate-related hazards, including river floods, coastal floods, droughts, and epidemics, and the distribution of exposed populations. The population projections derived from SSPs are also applied to non-climate natural hazards such as earthquake and tsunamis, and non-model hazards, the cyclone winds. Population and other socioeconomic projections, including economic output, education attainment, history of conflict, and some others, are used to project the human hazard component of INFORM. It is also possible to incorporate analogous modifications into INFORM subnational models, since the hazard and exposure data are analyzed at very fine scales. These are two main results of the INFORM climate change analysis: change in risk and vulnerability gap. To explain more in detail, changes in risk refers to changes in risk scores under each scenario combination in certain time span relative to the baseline risk scores, and the vulnerability gap shows the change in vulnerability and lack of coping capacity required to maintain the baseline level of risk. The increase in vulnerability gap implies that countries should invest in adaptation measures to maintain current risk levels. On the other hand, decrease in vulnerability gap shows that those countries would be able to keep current risk levels even with higher vulnerability and lack of coping capacity levels in the future. So, with minimal investments in adaptation measures, they could be able to scale down the risk class. In this study, we consider a large suite of 5 scenario combinations, namely RCP 4.5, SSP1, 4.5 SSP2, 8.5 SSP2, 8.5 SSP3, and 8.5 SSP5. In this way, we are able to expand the uncertainty in future climate changes and provide a challenging yet plausible scenario context to inform the climate change adaptation and disaster risk management strategies. In this slide, you can see the changes in risk under best and worst combination of scenarios in 2050 relative to the baseline risk shown on the left. The largest changes in overall risk are generally projected in parts of West and Southern Africa, South America, and Western Asia. Now in this slide, you can see the vulnerability gap under best and worst combination of scenarios in mid-century to keep the baseline risk levels shown on the left. The results reveal that countries in Africa, South America, and Western Asia generally tend to experience large increases in vulnerability gap in mid-21st century. Therefore, they need to heavily invest in capacity building to be able to cope with future impacts of climate change. Informed Climate Change tool provides insight into the result of the climate change risk analysis. It is available in beta version on Inform website. It helps the users to easily navigate within different scenario combinations and different points in time, exploring the potential changes in risk, hazard and exposure, variables, and population. It includes 4 main features: fact and figures, key changes, hazard projections, and country profiles. The fact and figures provide information on global distribution of countries by informed risk classes, income group, and regions under various RCP-SSP scenarios for baseline, 2050s, and 2080s. The same approach is used for all three dimensions of informed risk, hazard and exposure, vulnerability, and lack of coping capacity indices related to vulnerability and lack of coping capacity do not undergo any modifications and are directly adopted from Informed Risk 2022 release. The Key Changes tab visualizes the changes in risk, hazard and exposure, natural hazard, human hazard, vulnerability gap, and population density relative to the baseline under various RCP-SSP scenario combinations. The hazard projection feature allows comparison among different scenario combinations and/or different points in time for each hazard, climate-related, non-climate, and non-model. Here you can see the global distribution of drought risk for baseline and RCP 8.5 SSP3 in mid-century, and here the conflict risk under SSP3 scenario. And finally, the country profiles contain more in-depth information on each country in addition to the results in global list. Country risk profile shows scores for each risk dimension and hazard and exposure component under various scenario combinations for baseline, 2050s, and 2080s. Here you can see the Afghanistan profile for baseline RCP 8.5 SSP3 in 2050. As the way forward, the index can be improved in many ways. The hazard and exposure projections can include a larger suite of climate change scenarios, projections of heat waves, urban flood, and extreme winds. Also, the data can be replaced with the ones based on new generation of climate models, coupled model intercomparison project Wave 6 models in the future. The team is currently exploring ways to incorporate available SSP-based projections of various drivers of vulnerability and coping capacity such as socioeconomic variables, including HDI, poverty, headcounts, Gini, etc., migration flows, governance, urbanization level, and infrastructure. Integrating such projections into the Informed Risk Index would be an important contribution for its partners in terms of horizon scanning and global humanitarian risk monitoring. If you want to find out more, please visit Informed website. Thank you very much.
Thank you. SEPAR is online, so if there's clarification questions, please raise your hand. None at the moment, but thanks for being online. Then I will move. Yeah. Tabea will take over.
Great. Yeah, thanks a lot for all of these excellent presentations and also keeping in time so we still have a bit of room for discussion. In our session, we actually also have 3 posters that are part of this mix, and we actually have 2 of the poster presenters here in person, so I would ask them actually to come up because we've asked them to both have like a 2-minute pitch for their posters so we can also take that into account for the discussion. So yeah, Giacomo and Alessio, if I can ask you to join, and do we actually have 2 more? Yeah, both. I mean, I can, yeah, if you just want to take turns here and then, yeah.
Yeah, hi everyone. I don't have materials yet to show, of course, but if you come later at the poster session, I will be presenting to whoever is interested ongoing work on projecting future demand for electricity induced by future uptake and utilization of air conditioning at a global scale, in particular working with microdata and projecting household level future changes in consumption. This means that projections are reflecting a lot of possible sources of heterogeneity of drivers of autonomous adaptation in terms of cooling services. To provide some examples, cooling uptake and use are driven by changes in income, of course, but changes in climate, but also other interaction between micro and macro drivers, such as education, age, housing quality, and other determinants, urbanization, of course. And so in our study that we are developing, we are building a large sample of household data from different regions of the world to try to explicitly model these dimensions together and to provide estimates of what could be the future energy demand under different scenarios for air conditioning, induced by air conditioning use. And this is, of course, ongoing work, so I will be really, really happy to have your feedback and views on this piece of work later. And thank you.
Hi everyone, my name is Alessio Mastrucci from IIASA, and our poster is focusing on what we call the cooling gap, so adaptation to heat stress, focusing on the residential sector. So we have heard also from the previous presentation that heat stress is a growing concern for many parts of the world for its implication on the health, population, and also on the well-being. So there is also for the global south, where we have severe climatic condition and low income levels in many countries, there is a lot of concern, and despite projected growth in access to cooling and air conditioning, it is highly uncertain in the future how many people will have access to cooling, to basic cooling where needed to prevent heat stress issues. So we used a bottom-up model called MessageX buildings to project the lack of access to cooling and to understand also in which regions population might be more or less affected to this issue, also across different SSPs. And we also calculated how much energy it would be required to provide basic cooling to everybody in the global south, and how this amount of energy can change also under different scenarios and also under different technological developments, including improving AC efficiency or also the quality of housing and slum eradication. So I invite everybody to check for the poster, and happy to also tell more later at the poster session. Thank you.
Great. Thanks a lot for quickly being put on the spot and giving us a short overview of your posters. Could you put up the slide again? Great. So as we mentioned in the beginning, there's a few, questions that we've had in the back of our heads when also developing the session. So we'd be really keen to discuss a little bit and hear reflections. But obviously, now with all of the absolutely excellent inputs, thanks again to all of our speakers, of course. I'm sure there's a lot of additional, thoughts and questions that have come up, and I'll just take the liberty of having the microphone to start off with, one broader question that really has come through for me also through these presentations, especially also then in the beginning, but really sequencing through, is also the adaptation pathway approaches and these kind of ideas kind of start with a certain set of adaptation measures that we identify and then put into our models. But of course, as we well know, things change over time, and we have different, that's what the pathway approaches are for. So how do we actually take into account the potential limitations of these options, and how do we then identify potential other opportunities or other options to take into account to overcome those limits? There might be, regional differences in preferences or in approaches to, so how can we really be flexible enough to really take that broad perspective into account while still being able to actually implement that into models, operationalize it, and then move that forward to then also integrate that into the scenario space. So I'd be really interested to hear hear thoughts about that, maybe to kick off the discussion. And maybe I'll just direct it to you first, since you started out with adaptive pathway approaches as well, if I may. But I'm also happy to, yeah.
Well, what I think is very important, I mean, coming from my presentation, right, to pitch, to incorporate the anticipated future learnings into the approaches, maybe I actually have a question regarding to this, because I'm not coming from the science community with integrated assessment models, so I am assuming that incorporating the future learnings is until now not happening in the models, but maybe can I address this to you if this actually, does anyone know if this is actually something that is done, or is it not happening so far?
Do we have some IAM modelers in the room? To also address the question of, yeah, where are entry points for adaptation and adaptive capacity, actually? Huh? Matthijs?
Hi, I'm Matthijs Harmsen from PBL. So to answer your question, I don't think, at least for the image model, I can say there's a clear way to incorporate future learning, as far as I can say. So we had a look together actually for within the Navigate project, also taking image as an example, looking a bit at what is there actually in terms of adaptation and also impacts. Was also related to specifically an impact study, and I think we could conclude that it's very discreetly in there. So adaptation is either fully in there or not at all. So it's a bit of a weird mixed bag. Yeah, also like even for our standard scenarios, impacts first of all aren't really fully in there, but also in a way they are. So for instance, CO2 fertilization or placement of like land allocation. I think impacts on renewable energy, those are, for instance, in there. Definitely, usually not impacts on economy. So it's a bit mixed. And then if impacts are in there, then you can either have a full impact, so no adaptation, or total adaptation, so there's actually no impact. Or, for instance, in the case of heating and cooling, that's fully taken into account with air conditioning, and I already understand that's very unrealistic, for instance. So this just to give you a bit of an idea of what is in there, but I think we did find quite a few entry points. I think in many cases adaptation, for instance, for that exercise we implemented way more impacts, so I think there you can do a lot. Then in many cases you could have an idea of what kind of adaptation you could expect, or have assumptions there at least, so you could, I think, be much more comprehensive there. But I think Detlef actually mentioned that point that you introduce quite a lot of uncertainties, or you disregard those uncertainties altogether. So climate sensitivity, or so what kind of impacts would that imply? So you have way more uncertainties, but I think and then I'll stop, sorry. My take on this is there's a few huge advantages which you otherwise will never have, mainly in the form of interaction. So you have all these impacts introduced, some assumptions on adaptation, so those will define the final impacts, and those have all sorts of interactions within the model. And that's something you otherwise won't have if you have two groups, I think, and those will always be incomplete and have a very soft link. But if you do have everything together, then you have loads of uncertainties. The question is if that's better or if it's more comprehensive. So that was, in short what we think, what we concluded even, yeah.
Yeah, I think K1 would like to add to this.
Yeah, so perhaps adding to what Matthias said, I think models who represent certain biophysical relationships, like the water needs for agriculture, they can adapt simply by investing into infrastructure, and that will happen. So the adaptation, the response to climate change is endogenous, and there is normally no limits to it. There is also in many of the models, then the more difficult part is, I think, even the adaptation in social systems, right? So what is how to adapt in case of threatened health, and what do you do with the health system? How do you adapt to those type of incidents? That's even more difficult, is completely missing integrated assessment models. And I think what would be really nice from this type of studies is to get a better understanding under which, let's say, socioeconomic or development conditions, where are the limitations to adaptations? Where are the limits to adaptation under different circumstances? And to have this in a very systematic way would be really helpful, because one could then perhaps add this also to the integrated assessment models.
Any reactions from our panel?
On K1's point, maybe ask a specific question. So to illustrate what we mean, ask Esther, for example, in the agriculture sector, you even had on your concluding slide that there could be limitations to your adaptation possibilities, and you mentioned mitigation or reforestation, restoration rates. Could this parameter, for example, take into account different levels of socioeconomic development that would in a way constrain the possibility of your adaptation taking place?
Yeah, so maybe reflecting to both. So I think it would be possible to, if you have a certain SSB or you have a certain more sustainable pathway, where just coming from the land perspective now, you have a certain amount of land that you want to allocate to restoration, right? And you have less, of course, you have more competition for land, maybe less opportunities to go for extensification, and maybe more pressure towards intensification. Maybe just reflecting also to the point from K1, I think maybe one of the big challenges also, I don't think that I'm working with an IIAM, but is that we, even when adaptation, when looking into endogenous adaptation options, we're putting in a single shock or a single driver into the system. And I think that the real challenge maybe lies also in sort of like the increased uncertainty, especially when it comes to maybe sort of the more extremes, and how to sort of like being able to have equilibrium models or IAMs being shocked in such a way that they would take into account that there is a range of maybe positives and negatives, rather than to have just this one biophysical factor change or so. Maybe.
Thanks. So I guess on this impact of resolving impacts in the IAM, so like beyond resolving any individual process, any individual impact, there's like relating to the first talk, what was really being presented there is a way of sort of like hedging on the future, sort of like being presented with a probability distribution which reduces over time. And in order to get at that, then the way that we solve for scenarios in terms of least cost trajectories towards some sort of target is, we have to revisit that entire question, right? I mean, that's, if the future-looking nature of the integrated assessment models is a problem for the framework, the defensible framework that you presented, because at any point in time, you need to know not where the model is solving for in this particular realization, but every possible state of the future. And unless we have that, unless we have a scenario, probabilistic scenario system like that, we can't get at that kind of question.
yeah, I think we can have a couple of more questions, and then yeah, we're reaching the end.
Yeah, hello, Johannes Emmerling from AIE. I want to raise 2 points. One is on the question on the learning. So I think in most IEMs this part is not considered, and I mean the main problem being that these models getting increasingly complex, doing a stochastic analysis like you would have needed on a real dynamic kind of stochastic programming, dynamic programming approach. I mean, has been done on a global model, very simplific models, but I think at these models, it's one of the big challenges. So the question is how to simplify or use Monte Carlo or other kind of simplistic approaches to do that. That's maybe the way one. On another one, and I think this is one of the big questions forward in this whole topic, at least from my point of view, is the link, and it was nice to see some of the presentations here on different indices of the adaptive capacity, like the last one by Sefer, also the one on Scotland. I think it's very nice to have this data on adaptive capacity now being more and more available, including in the RCP SSP framework. Now what I missed there is a bit the link to the outcome variable. For instance, in the case of you showed the mortality, I think so you have the nice figure of temperature versus mortality, and you have it over time and how it changes basically, and you say this is due to adaptation. Now what we miss, I think, is a figure where we have mortality and the adaptive capacity index. Now this would really be a way forward to then include in the model to say, okay, so what if, let's say, different SSPs evolve according to different storylines, quantified, etc., and then how does it change the impact, how does it change residual impacts, and how it's linked to adaptation costs. So I think that's really, I mean, one sees it goes in this direction, but I think that's really a missing link at this point, I think, in terms of integration in IAMs. Yes. Thanks.
Eva?
Okay, I hope this works. Tying with this, maybe taking one step back from trying to implement adaptation in models, I just want to say that as a first step, we need to understand what adaptation actually looks like and how it already takes place, as it's very heterogeneous across impacts and across countries. And as we heard about air conditioning, I mean, we need to understand how in different SSP developments, how degrees of urbanization actually and socioeconomic indicators impact the demand for aircon and therefore energy demand and potential maladaptation. This holds also for irrigation, where different RCP developments play a role. So we need to know whether water demand can actually be met. So I feel that before trying to, and this is just something that I realized when trying to model these adaptation actions, they're so heterogeneous and they're so dependent on socioeconomic and climatic developments. They really need to talk to stakeholders, talk to farmers, talk to people who are experiencing heat stress, how they are actually planning on doing that. And I think that only when we know how this will evolve, we can make up our minds on how this actually enters the models, to have this, to capture this heterogeneity, and move away from this assumption that adaptation is endogenous and just happens as a response to relative price changes, and really shape adaptation pathways in a sustainable and equitable way.
Perfect. Thanks a lot for these last remarks, because they're very close to a lot of the final points that I actually wanted to make to wrap up the session. First of all, thanks a lot again to all of the speakers and to all of the discussion intervention. I think it was a really, really interesting session, and I guess more of a starting point and an opener for a lot of the absolutely essential points that we do need to address. I guess maybe just a couple of points to add to what you were just saying. I couldn't agree more that we really need to look at the context, and I guess coming from the working group too, and having been part of a lot of the adaptation assessments there, is that, yeah, what we know about adaptation is actually very little. We know it's taking place, but we know also it's fragmented, very context specific, and exactly those preferences of how you would actually want to adapt to a specific situation on the ground obviously differs substantially, and you might still, be looking at the same outcome, and how we actually are able to represent those preferences and choices in the aggregate manner that we actually need for the scenario space, I think is really something that we need to resolve at a kind of, at a different step. What we definitely see in terms of adaptation quantification basically is exactly that. What we are able to quantify are very specific options like irrigation, like energy, like air condition. These are not necessarily the sustainable options, but also we completely neglect the largest space of adaptation that actually has been shown to be effective and been used in practice. So really how to resolve that, I guess, is a huge question. So I'm really looking forward to continuing a lot of these discussions. In many more sessions, and I guess now over coffee. Great. Thanks a lot.